Welcome to another Founder Wisdom Pod. We have David Patterson with us. David is a computer pioneer and academic. He held various positions, but his main one was professor of computer science at University of California, Berkeley since 1976, that is. He announced retirement in 2016 after serving there for nearly 4 years, which is quite a lot of time, becoming a distinguished software engineer at Google. And he is currently vice chair of the board of directors at RISC V Foundation. I discovered personally about Dave through the Lex Friedman pod, and hopefully we're gonna start with a short technical discussion on what David has been doing and is doing nowadays, and we will switch to a beautiful document that David sent me called the 15 Life Lesson from the first half century of David's career. So lots of good lessons in there. This podcast is presented to you by podpire.com. If you want to start or scale your own podcast, go to podpire.com. David, welcome to the pod. Tell me a bit more about yourself and about what you're up to nowadays.
Well, I guess about myself, I'm a Californian. All my education was here in California. Grew up in Southern California on the beaches there, body surfing and having a good time. I went to UCLA and got my bachelor's, master's, PhD, and then was fortunate to be able to get a job at UC Berkeley, where I spent 40 years. And since then, I needed to slow down some, so I took a job in industry, and it's kind of like being a grad student again. I get to wear running shoes, t-shirts. I get to pick what I want to work on. I don't have to finish a dissertation, so I'm having a great time.
40 years at one place, how does one accomplish that? Was the academic career a natural fit for you? Did you fit right in your place? How did you stay there for so long?
Well, yeah, I guess loyalty is one of my characteristics. I think I've only had 5 jobs in my whole life. I was a newspaper boy, and then when I was a teenager or younger, and then I worked for my dad's company in downtown Los Angeles, and then I had worked at UCLA as well as a grad student, and then Berkeley, and now Google. So I think I tend to stay in one spot. For me, academics, I love teaching and I love doing research. So Berkeley was just a great spot for me. And of course, it was, in retrospect, being at Berkeley, right next sort of Silicon Valley from the 1980s for decades. But that was just a great location to be. So I was very fortunate to be there.
Where did your fascination for computers started?
Yeah, it's a kind of a funny story. That back this, so I graduated from high school in 1965. There were no computers in high school. Actually, at UCLA, there was no computer science major. There wasn't even a computer science department. They formed the department in about my junior year. So I was a math major. I'd done math in high school and done well and done it at college. And then the math class was canceled my junior year. So to fit in my schedule, I found an introductory computer course just to fill out the schedule. And I took it and I loved it, even though it was amazingly primitive by today's standards, with punch cards and line printer listings. They still had that excitement of seeing the ideas come alive in your mind and having the computer follow it. So it's kind of like an really old video game. Like, how could people ever play this game? But at the time, it seemed really great. And then I kind of made an informal computer science undergraduate degree by taking business classes and the College of Engineering classes. So that was my introduction to the field. It was a math class was canceled. It wasn't some inspiration.
And I guess you were in similar times to young Bill Gates at this time. He took the corporate route, the startup route, that is, decided to go the capitalist route. Why did you take the academic and research route?
While I was finishing my PhD, I read a book that surveyed people's lives and how they felt about their careers. The book was named Working by Studs Terkel. And what I got out of that book is when people look back at their careers, kind of like the stage I am now, is the people who worked with people felt really good about what they did. So like ministers or doctors or teachers. And so I went into this expecting I'd feel good about what I'd done if I got to work with people, help young people. And that was a projection only about 50 years ago, and it turned out to be right. And I'm very happy. The things I'm proudest of is where I was able to help people, as opposed to the technical things are nice too, but it was the people thing that makes you feel good about what you've done.
What about the research route? Because a bunch of business moguls at some point they develop a research side to the business. I mean, Google was one of these, Microsoft certainly as well. They develop a fascination to trying to advance human knowledge forward. So I guess you had that, but in your case, my question for you is, how do you determine what you're gonna research about? Do you just let your curiosity run wild? Do you consult colleagues? Do you sift through a bunch of articles to decide what you're gonna focus your research on?
Yeah, we kind of came up with a formula at Berkeley after the success of the RISC project, and trying to figure out how to go forward. We thought in academia, since the people who work for us are there, their job is to stop working for us, right? They're to graduate and trying to get their PhDs, and they kind of last about 5 years. So we made a series of 5-year projects, kind of matching a grad student's lifetime. And then we wanted to try and change the world. So we tried to look down the road, say, what might the world look like in 8 or 10 years? And what new technological opportunities are changing that might let us have a high impact research result? So that was the approach we took. And we felt that in academia, by being multidisciplinary, we had a greater chance of innovation versus industry, which has tremendous resources in dedicated areas, but going across disciplines is harder. So we looked for kind of every 5 years a new potential research project that could have high impact, taking advantage of the strengths of the Berkeley grad students and faculty.
What's a computer for you? I have an M3 Mac in front of me. I consider it to be an assistant, a brain, in some shape and form, an incredible tool for sure that amplifies me and who I am. What do you consider a computer to be when you look at it?
Hmm. Uh, I think of these days, I think of stuff as more being in the cloud. I think, I've been using Google Docs partly because I'm at Google, but it's just wonderfully collaborative tools. I found that the skill of writing well still matters a lot in industry. And so what I try and do to try and, shift ideas inside of Google is write relatively terse documents, 1 or 2 pages so people read them. But what's really great about the commenting features of Google is you can get, dozens or even hundreds of people to read it, leave comments, you can respond to the comments, make changes to the document. So it's a living document. And I think it's an effective way to try and force change as you go along. So I think now it's more like my laptop and my screen is my path to the cloud, and what I'm doing is logically in the cloud more than what I carry locally with me.
A computer has a memory. It has sort of brain power as well, can be very fast or very slow depending on how much stuff it can process at the time. Let's start with this. How has computer architecture shifted from your time to nowadays?
Yeah, it'll be a little bit longer story. So let me tell you about what RISC is RISC stands for Reduced Instruction Set Computer. So what's that about? What's an instruction set? Well, when software talks to hardware, it uses a vocabulary, and the words of those vocabulary are typically called instructions. And they, just like the keys of your keyboard, add, subtract, multiply, and divide are examples of instructions. And so the technical name for this vocabulary is instruction set. So the reduced instruction set computer idea from the 1980s was that given Moore's law and the rapidly changing, improving capabilities of microprocessors, it makes more sense to have a vocabulary that's a lot of simple or reduced instructions rather than really complicated instructions. You can think of it as monosyllabic instructions versus polysyllabic instructions. So the bigger computers use these more powerful instructions, but we thought it made more sense for microprocessors to use these simpler instructions, and because we thought it'd make it easier to build them and they could actually run faster. And that's what the reduced instruction set was about. So that was how do we design microprocessors in the 1980s. If we look today, what it's really kind of amazing, since I joined Google 7 years ago, is I was put in this part of Google that was interested in machine learning. And when I joined, I didn't know much about it. And it was hard to know how significant it was. But kind of every year since I've been there, the machine learning or AI has gotten bigger and more exciting. And in this last year, with the release of ChatGPT, it's kind of exploded. And so I think we're at this, tipping point in time, which is I can hardly believe I'm going to say this, where it looks like going forward, the standard central processing unit that we've known, the von Neumann computer that we've known for the last 70 years, may play a less important role than these specialized hardware for machine learning, specialized hardware for AI. The companies, maybe the way they're investing, and that maybe the more important things that are happening, the applications of the future, are going to be running on these AI hardware rather than the traditional central computer. Which it's a remarkable statement, because think of all the advances that computing has brought about in the last 75 years, using the standard von Neumann computer. That this idea that special domain-specific architectures just for machine learning and AI may play a more important role in our society than general-purpose computers is pretty remarkable. I'm not saying it's positive, but it's plausible that we're at this tipping point.
We're gonna get to that. I want to make sure also that my brain understands, for example, the difference between hardware and software. To me, hardware is less malleable, but software is still something physical, right? It's energy, it's bits and bytes of communications, it's electricity, it's me typing energy from that keyboard and to this machine so that it understands and process and replies something back in exchange. So am I accurate in saying this?
I don't. I mean, certainly, code has to be represented as numbers. That's certainly true, and it has to be stored somewhere when it's not running. But I think, you can think of almost, like I said, software is almost the physical realization of somebody's ideas. A programmer has what he or she wants to do in their brain, and they try and get it out through writing, lines of code, and it is compiled and turned into bits that we run on computers. So it's kind of this funny thing that's both kind of ephemeral and physical. And this machine learning approach to doing AI is this idea that rather than writing millions of lines of code to get something useful, we can learn from millions of pieces of data. So that's this kind of, like I said, this big paradigm shift that people are excited about. And the question is, how far is this going to go? So software could take a very different form going forward, depending how pervasive machine learning and AI is.
And is computer science, hardware and software, the human trying to reproduce a brain, not a super intelligent brain at first, right? A brain in which you can command things. And arguably, I can still command stuff to my brain and it will follow and execute these tasks. But if we picture hardware and software, it's hard not to think about the brain being the hardware, and the software, the electricity that goes through it, the neurons that get fired, and the biochemistry in there.
Yeah, that's probably the right kind of analogy. The brain is probably the computer, and your intelligence, the way the neurons are wired together, is probably what we think of as, that's probably where intelligence is in the body.
Right.
That seems fair.
And AI being finally giving that brain a couple more IQ points, or like multiplying the amount of neurons in the cluster inside it.
Yeah, so it's this is I mean, I can't emphasize enough how quickly it has changed in the last few years. Is maybe 10 years ago, if you surveyed people in who are, I'm not an expert in AI, I'm just helping to do hardware to make it run better. But if you surveyed AI experts, when would we have computers that reach what's called, they call artificial general intelligence, so that you'd have something that could do many tasks. Right now, in the past, we've had kind of idiot savants that, boy, if you wanted to play Go, this thing could play Go better than maybe any human could, but it couldn't play checkers or something like that. So how about something general purpose? And so when would we get an artificial general intelligence equal or better than humans? And they, the estimates were many decades away, and that's been brought in quite a bit. And just because of the progress in the last years, these projections, so they may not be right, but this idea that we could get something that could do many things at or better than what humans could do is a pretty remarkable hypothesis.
Right. And that's AI's directly dependent on the hardware/computer
Yeah.
architecture that you're behind nowadays. I picture an Nvidia chip when I think of modern AI computer architecture. What has happened in that chip? Has it just gone better, or have we fundamentally changed the architecture of the thing?
Uh, I would say it's been tweaked, maybe. So what happened is kind of the history of this is these ideas that what we call machine learning. It's kind of like well, let me do the circles. The big picture. I see my hand. Okay. The big picture is it was AI. That's what it was called in the 1950s. And inside that, there was this group that said the way people are thinking of AI, of writing rules top down, that'll never work. Humans can't do that. We have to go from data and learn from data. And then within the machine learning group, there's this other rebel group that believe that the only way you're going to do machine learning is by imitating the brain, by making artificial neural networks and learning from labeled data. And that's the part that has just started working in the last 10 or 15 years. The algorithms have been around since the 1980s, but finally thanks to cloud computing, we had enough data, and thanks to hardware advances, we have fast enough hardware that suddenly these things started working well about 10 years ago. So it turned out that of the various computers that you could get your hands on 10 years ago, GPUs designed for graphics had pretty good floating point computational arithmetic performance per dollar. They were pretty good at that. And so for the first like 5 years, they were just using off-the-shelf GPUs to make big advances in machine learning. Once Nvidia recognized that this was going to be an important market, they brought out a GPU with special features to make machine learning run ever better. And so that was 2017 when they brought out, or 2017 to 18 when the Volta came out. That was the first GPU that actually had features for machine learning. And since then, every year or two, there have been new GPUs that are even better each year for machine learning.
What were these features? I can certainly picture it overheating a bit like the brain, like it's just too much data and, I don't know what to think about anymore. Not sure if that was the best analogy, but these computers, they do overheat. I know that my M3 right now, it does overheat at some point. So was it energy dispensary? Like what were these physical features made for AI?
Yeah, so what happened is, well, let's do another big picture thing, right? There's Moore's Law, which has been around since, of the 1960s, and it lasted for 50 years, where you could keep doubling the number of transistors, the kind of the switching circuits that are the foundation of computing. You could double them every year or two for 50 years. Well, how could you keep doubling the number of transistors without the thing using up all the heat in the world? Well, there was this other corollary that's less well known called Dennard scaling, and basically you could make the transistors more efficient, more energy efficient every time you doubled them. So it actually, for decades, it stayed relatively flat. After all that advances, this idea that's called Dennard scaling stopped kind of 20-ish years ago. So now we can get more transistors, but we're using more power. And so what you've seen, especially in the last decade, where microprocessors used to be 5 watts, and now they got up to the limits of air cooling, which is 200 to 300 watts. And then in data centers, they've gone past that. You can see things at 500 or even 1,000 watts where they use liquid cooling. But as we, to make things go faster, they're using more electricity and generating more heat, which is why you're seeing that on your laptops, or if you had a GPU under your desk, that would be using, generating a lot of heat. So it's just basically, if we still had Dennard scaling, if Moore's law was still in great shape, maybe we could have continued without using more power. But now, most of the innovations use more power to go faster.
Right. What are other factors in Moore's law? The advancement of technology, the reducing of the cost. So there's a capitalist aspect to it and a market aspect to it. The cost of electricity, the wires and the technology to transit stuff faster. I guess, what are all the factors compounded into Moore's law in your space?
Well, basically, when Moore made his observation that it looked like for the last few years we were doubling the number of transistors every year or two. The equipment that makes that happen is the semiconductor processing equipment, and you need new equipment to make smaller transistors every few years. So it became a guideline of investment, is that if we were going to stay on Moore's law, we had to be buying the next generation of semiconductor equipment each time. And to make the finer and finer transistors, the equipment got more and more expensive. And so the only way that made economic sense is if the volumes of chips you made go up. So that was true for decades. And almost every generation or so, the equipment you bought became twice as expensive almost. But as long as the volumes went up, everything worked out okay. So this has started kind of falling apart in the last decade, where the equipment's getting so expensive, it's getting so much harder to design these smaller transistors, and the transistors aren't that much better than the last ones. We've ended up with fewer and fewer companies who can afford to manufacture microprocessors. So that's kind of there's an economic engine that's behind these advances we've been doing, and it's beginning more expensive, more difficult, and so there's fewer companies that can make chips now than there used to be.
How can you make a chip interact better with software? Is it just, as you mentioned when we started, about simplifying the language inputs it can take?
Well, the big thing that's happened in about the last decade is because of the slowing down of Moore's law and the end of Dennard scaling, general purpose processors, which used to make giant strides in performance every year, have started slowing down. And so, in the last century, if you had a laptop, you might throw it away every 18 months because even there was nothing wrong with it, but your friend's laptop was so much faster and better at the software that you were envious and threw it away. So that stopped happening. But our software colleagues still have this thirst for faster computers, in particular, machine learning. The first word machine learning is machines. They need faster computers. So Moore's law is slowing down. We're running into energy limits. What are we going to do? And so people who, like me, who design computers, which we kind of flatteringly call computer architects, think the only path forward is what they call domain-specific architectures. That is, it can't run everything well. It can't run Excel and Word and browsers. But if you just tell it to do machine learning, it can do that really well. So by narrowing the focus of what types of applications you can run, we can make big strides going forward. So that happened. And then the question, well, we were stuck. The only way we can make better computers is making domain specific. What domain are we going to pick? So like about 10 years ago, this is what was starting to happen in computer architecture design. And, fortuitously, machine learning exploded on the scene. So we were forced kind of by hardware to do domain specific right when there became a domain that looked to be incredibly valuable. So that was just good fortune. And then Nvidia happened to be at the right spot in the right time to have a pretty good starting point. And then they made their GPU, which is the GPU stands for graphics processing unit. So it was an early example of a domain specific architecture. Now they made that architecture also work for the domain of machine learning. And so what's going on right now, that's why I said we were at this tipping point where now we know how to do domain specific architecture for machine learning. Perhaps machine learning AI is going to become even more important in our data centers. So maybe more of the money is going to be spent on hardware for machine learning than we've ever thought about in the past. So this very exciting times in hardware design and business and applications, and it makes it really fun to work in the field.
Because for consumers, let's take my M3 and this Google Chrome. Every now and then my computer crashes because I just scale way too much for a consumer made computer. It seems to me that the future, well, at least consumer wise, would be to just receive the output of the AI. And as a business, it would be valuable for me to buy as many chips or pieces of an Nvidia data center somewhere. So you just outsource the crunching to that big company. Is there still advantage as a business to run my stuff locally, or is that only useful for academics and researchers like yourself?
Yeah, what you're talking about is cloud computing. That was one of the things I worked on for a while, and we made the argument that there's a lot of advantages to having for cloud computing, and that you don't have to have your own data center and maintain your own hardware and things. And they're able to, in particular, it has this economics, it has a scalability, which is amazing, that if you wanted to use 1,000 GPUs for an hour, you could just do that. You could just go to Amazon or Google or Microsoft and rent them for 1 hour. And so there was this incredible scalability. This before cloud computing, you if you didn't have the budget, you'd buy one GPU and had to wait 1,000 times as long to get the answer back. But for kind of the same cost, you could get 1,000 of them and just rent them for an hour, and that was okay. So it's a brand new idea, kind of computing as a utility community. I certainly think it's very attractive today for many people's situations. Some people have enough steady work that they can afford to just have their own local data center, and they can save money that way. But I think for a lot of people, the fact that like when the new GPU comes out or Google's TPU comes out, you can just spend your money on that rather than, you don't have to buy a new one and install it. You can just go to the next one. And in this domain-specific architecture space, each generation of new accelerator makes a big step forward. So I think, yeah, there's a strong argument for doing things in the cloud as opposed to having your own personal copies of the computers.
If OpenAI has a software moat and Nvidia has a hardware moat, where does Google stand into that?
Yeah, good question. Google has both. I mean, long before I got there, Jeff Dean, who is one of the superheroes of Google, one of the main engineers there, had this insight pretty early that he thought machine learning was going to be a big deal. He had played with it, and particularly the neural networking stuff. He had played with it when he was in college, as an undergraduate, and he thought, oh, that's pretty interesting. I wonder if that's going to go somewhere. And so he, maybe 15 years ago, started to have the insight that I think neural networking might be starting to work now. So Google, he said, and around 2012 or so, he said, boy, I think if 100 million of our users started using this machine learning stuff, we'd need to double our data centers. And so that would be very expensive and take a long time. So that led Google to start their own hardware program, which we call the Tensor Processing Unit, TPU. And the first TPU was, I think, started around 2015, and I was in Google data centers in 2016. So we actually had special purpose hardware for machine learning in Google data centers before Nvidia brought out their hardware for a GPU with enhancements for machine learning. So Google is very early on in that. And then it's also been early on in a lot of the software stack. So, you know, the good news is Google isn't has its own option of where it can get hardware from. It does buy Nvidia GPUs, but it also has doesn't isn't forced to buy GPUs. It has its own alternative source, and then it makes those things available in the cloud for people who decide which one they want to use. Would they rather use GPUs or GPUs? So that's the situation we're in. Other hyperscalers have followed Google's lead. So Alibaba, Microsoft, Amazon have all announced their own custom accelerators for machine learning. So that's kind of where we are now. The hyperscalers tend to have their own. Most people outside of the hyperscalers use GPUs for what's being done, and there's a bunch of startups that are trying to compete with Nvidia to make hardware that you can buy and use yourself.
Couple of rapid fire for the last 5 minutes. I have your 15 lessons document, which you'll eventually publish. They're really, I love the document, really concise and a bunch of cool lessons in there. Number 5 is seek out honest feedback. Most people find it hard to take feedback. How does one do that without like having their feelings hurt?
Yeah, well, it depends. It's most people, because you don't want to get your feelings hurt, you know, you avoid it, avoid people. But you know, if you're in the business of ideas, this is the way you get your ideas better. So my view is, hey, you get all these people to help you make your ideas better, and what a great opportunity. So when I was an assistant professor and I was working on the early RISC ideas, I realized, wow, Silicon Valley is just a few miles away. We were doing all the students. We'll invite experts from Silicon Valley to critique what we're doing, and that'll make them better. And so and when you're an academic, a big part of what you do is write papers that you're trying to convince people that this is a really great technology, and you try and get them to adopt technology. So if you're basically trying to make an argument for something new, so why not show it to the people and get their feedback on what you're doing to make them better? So for me, it's setting aside your feelings, because when I write them, I think, wow, this is just about perfect. People are not going to say anything. They're going to say, wow, there's nothing wrong with this paper. It's perfect. Every time I go into it, but it doesn't turn out that way. But it makes the paper better, and you can avoid mistakes as opposed to you put the paper out without that feedback, and then you can find out you made embarrassing mistakes or there's big holes in your argument. So it's been, it makes sense to get feedback on what you're doing. For the people in academia who don't do that, if they skip that step, the feedback comes from the editors, the reviewers, and then your first feedback is from the decision makers, and you may miss your opportunity. So to me, it makes tremendous sense, and you just have to make it clear it's okay to make mistakes and be pointed out, because they're helping you make your ideas better.
Last one. In a society that promotes fast and urgent, how can we distinguish urgent from important?
Yeah, that was that idea was when I did this document. Some of my former students made suggestions, and this was one about. I think that table about it's
the Eisenhower matrix, right?
Yeah, it's from the book on the habits of very successful people, and it's urgent and important and unimportant, and urgent and non-urgent. And you work on the urgent, important things. That's not surprising, but right there it is. Yeah. So the upper left corner you work on, but you often work on the not important things that are also urgent. And you never quite get around to the things that are important but not urgent. And the argument is, if you're going to be successful, you better set aside enough time to work on the things that are important but not urgent, because it's easy to avoid them. And that, when I heard that argument, I think that applies well to the way I've tried to do things. And particularly we make, as a community, we make this very distracting technology that you can spend a lot of time on, whether it's email or text texting or games or stuff like that. So it's very easy to avoid working on the important stuff that's not urgent. And it's hard to have an impactful career if you don't do that.
So what's important for you nowadays? What are your priorities this year?
Well, for me, it's partly going from being a professor to something else. I had to figure out what I wanted to do, and because I could have taken another prestigious job, but fortunately, I've already done one of those. So my guideline is to do more of what I like to do and less of what I don't like to do. So when somebody asks me to do something that I don't want to do, I say, sorry, I'm retired. And then if it's something I want to do, then I sign up for that. So at Google, it's an interesting company with lots of interesting challenges to work on. So I think right now, most of my time at Google, I guess there's two major focuses, which is how do we do hardware for machine learning going forward? This excitement recently about the large language models. They're very expensive, they're very powerful, and very expensive to serve. So this is like a perfect situation for hardware software co-design, because we desperately need advances to make it faster and cheaper so that more people could use it. And the other one is I've ended up kind of a hobby of talking about the carbon impact, the carbon footprint of machine learning. There are some, about, I guess, 3 or 4 years, 5 years ago, some articles came out that were startling in their predictions about how bad machine learning was for the environment. So I ended up trying to investigate those things. And that's been something I've been working on for a while. Yeah.
Dave, thank you for today. Where can people find out more about you?
I think if you just type my name in, look up papers about me, I think I'm on Wikipedia and most places.
There you go. Yeah, Dave Patterson.